power series as a function. So here is, it's question 13. I don't think they actually have a version of it, so they're all like this. And what makes this different is, have you noticed how few numbers there are? Everything is considered something like, there's B and there's A. B and A are called constants. That means we don't know what they are, but they're a fixed number, right? N is a variable because doesn't N, change value, right? So I'm going to go and do exactly the same process. And see what the radius of convergence is, and then from there, figure out what I should be. So it's going to be the absolute value of, let's see what we have here. N plus 1, x take away A to the N plus 1, all over B, N plus 1. And we agreed yesterday, and I don't think anybody said they didn't like it, that we can just turn the second guy upside down and save a whole line of working. Would it be fair to say that we're all comfortable with that now? I don't need to do ugly guy over ugly guy and then turn into that. So that is going to simplify, and then hopefully, get the limit. Okay, you tell me. I was about to do the answer, but you tell me. Something on the top, cancelling with something on the bottom. What's left and where does it go?
The B to the N and then the B to the N cancel, and then there will be a B left over on the bottom.
Okay, I'll do the next one. Would you agree that the x minus A to the N and the x minus A N plus 1 cancel, and there'll be an x minus A left on the top? So far, so good. I tend to leave these guys, these guys here to the end. And what we've got essentially right now, oops, it's an A. Is that agreed? Just shuffling the cards a little bit. These are constants, so I don't need to worry about them right now. Or at least I'm considering them constants. Would you agree that the ratio n plus 1 over n gets you 1? Can you prove it with L'Hopital or divide top and bottom? So that means that we get 1 times this, and our limit ends up being that. So do you see, it didn't matter that there weren't any numbers. Doesn't the process not really care that A is 4 and B is 22, right? You do the same math whether or not they are fixed values that you know or fixed values you don't know. Now, for this to converge by the ratio test, it has to be less than 1. So far, so good. But we don't want that, don't we? Need it to be written like that, agreed? Absolute value of x less than a number, or the absolute value of x minus a less than a number. So what do I do to both sides to get from this to what comes here?
Multiply it by b.
Okay. And now we know the radius of convergence, isn't it? B. Right, normally it's 42, but here it's B. Now, you want to get the interval of convergence, isn't it between B and negative B? And what would you do next is you would add A to both sides. Not quite sure why the order gets switched, but it doesn't matter. Agreed? A minus B, A plus B. Shouldn't we test the endpoints? Right. So the two endpoints are x equals A take away B and x equals A plus B. And here is the series. If you make x, this guy here, A minus B, you now get n, B to the n, and A take away B, take away A to the power of n. What does that become? Well, it becomes negative B to the n. If I pull out the negative 1, I now have that. You cancel the b to the ends and it ends up being this guy. Would you agree that's a diverger? Right? -1 to the n, isn't it? It's increasing, right? So not an n series that increases, that's enough to prove it diverges as well. So diverges. And if you do this one, can you trust me? It also diverges, but you can check it. Which means that our interval of convergence is any number from a minus b to a plus b, but you can't include the endpoints. Are we good?
On a test, would you want us to prove that n+1 over n equals 1?
Yes, you can do it as a little bubble at the side, right?
Got it.
You know, you would do something like L'Hopital. What am I doing? Try that again. You don't need the sigma for this one, right? Because it's a limit. L'Hopital 1 over 1 is 1, right? It would be basically that, right? It would be a 15-second write up. Agree they're not a lucky number.
Okay.
And have you noticed that almost all the ones that have n's or n squares in them that part tends to contribute to a 1. You notice that the n squared over n squared. So you kind of know it's going to be 1. Pretty much everyone I think we've seen at least. Any other questions before we move on to our next section? Okay. So our next section is, I'm getting its number, 11.9. And we're still on power series. And in this case, power series of functions. Interesting heading. Power series of functions. And I'm going to give you some magic in a few seconds. Magic just means I'm telling you it's true and you've got to trust me. Like 0 factorial is 1, right? You just got to trust me on that. Things. What's the other magic? Haven't I done 1 plus a over n to the power of b over n gets you e to the ab, right? Right. There's some things you just have to trust that are true. So here is some magic for you. One over 1 minus x, right? 1 over 1 minus x is in fact a power series. It's a Maclaurin series. It's actually this Maclaurin series. Would you have thought that the fraction 1 over 1 minus x was an infinite polynomial? Would that even cross your mind as a possibility? I don't think it would. For me anyway, it wouldn't cross my mind. I can't remember when I discovered this, but I do remember when I was told it, I didn't believe him. You know, my intuition said, yeah. But eventually I was convinced by experience, by actually seeing the thing working. Right. So are you okay with the magic so far? Right, I'm telling you it's true. So I'm going to try and prove it's true. That would be nice, right? So let's make S 1 plus x squared plus x cubed for eternity, right? Are you cool with that? And now I'm going to take S and multiply it by x. And so multiply that by x, multiply this by x, multiply this by x, and multiply this forever. Do you notice that the two infinite polynomials, those two series, aren't they almost identical, except this one doesn't have a 1 in it? Are you comfortable so far? Right. Now, I am going to take the top guy, S, and subtract from it the bottom guy, x times s. What would you get if you took this infinite polynomial and subtracted that infinite polynomial?
1.
Yes. Can you see where this is going yet? What do you think I should do to the left-hand side?
Factor out an S.
So what is S equal to?
One over 1 minus x.
Have I convinced you that 1 over 1 minus x is actually an infinite polynomial, a power series? Come on, that should be mind-blowing. How on earth could that fraction be an infinite polynomial? I mean, polynomials go like wobbly hills, don't they? 1 over 1 minus x is a vertical asymptote. They don't even look the same. Well, that's only because you only take this polynomial so far. If you kept on adding terms, the shapes of polynomials change. They stop looking like curly hills and they start looking like the sine function, or e to the x, or in this case, 1 over 1 minus x. In fact, every function that you know of, right, e to the x, sine x, log x, right, all those functions that you know, every single one of them is an infinite polynomial as well. And the next section will actually show you, you can find out what that polynomial looks like. But right now, we're only going to focus on these guys. And I'm going to take this fella and I'm going to rewrite him as that guy. Would you be comfortable that 1 plus x squared is this guy? Are you happy with that? Right, this infinite polynomial is that guy. This guy is much more, I don't know what the word I'm looking for, concise, right? Tells you the same, but I don't have to write all this stuff. So far so good. Now for every polynomial, right, for every power series, infinite polynomial that we have, can't we find its radius of convergence and its interval of convergence? Great. I'm just going to tell you what the answer to this is. Its radius of convergence is 1, and its interval of convergence is -1 to 1, but don't use the outside points. Now, can you prove that? Sure you could. I just won't go into it. Couldn't you do the limit as n tends to infinity of an plus 1 over n, and you do all the usual things, right? Okay. So that is provable, right? So you just trust me on that. So what this tells us is, yes, every function, and even this weird one, is an infinite polynomial, but it's only an infinite polynomial in the range of x's from -1 to 1. If you try and use it for things like x is 2 or -47, it breaks apart. So it's like a little snapshot of the curve. As long as you're between -1 and 1, this guy looks like him. So what we're going to look at now is a second piece of magic. Which is the fraction 1 over 1 plus x, and that ends up equaling this guy. This is a little bit harder to prove. I couldn't really prove it this way, so I'm going to prove it a different way, just to show that it's true. This relationship, we're convinced it's okay, right? You can use it. If you replace x with negative x, won't it become 1 takeaway negative x? But isn't 1 takeaway negative x 1 plus x? So if you replace substitution of x with negative x, don't you also substitute this x with negative x? And won't negative x to the n, when you simplify it, get you that? Can you kind of see it's a pseudo proof? That means that I can use either one of those two pieces of magic to find the power series, technically the Maclaurin series, right, of lots of fractions. But that means that we're going to have to learn a little bit about what you can and cannot do to sigma notation, right? You are allowed to do substitution. And you are allowed to multiply by constants and powers of x. We are going to use those two things that you're allowed to do to a series and manipulate fractions and use this to get the power series. So I'll start off with a real easy one. If I wanted to know what the power series of 10 over 1 minus x looks like, it would be 10 times that guy. Agreed? This guy is the power series there. And you are allowed to take constants that are outside this sigma and bring them inside. You can also do it the other way around if you prefer. And you will get n equals 0 to infinity 10 x to the n. And so there's your power series for that very simple fraction. Are we comfortable with that? How about this fella? I would like to know the power series for x cubed over 1 minus x. Well, I'm going to recognize it by rewriting it like that. Are we good? And now that I have this fella to work with, it's going to be x cubed times the sigma notation fella. Now, this x cubed is going to come inside. It's allowed to, right? You can bring x's in, you can bring x's out, right? You can do this. And so, all you need to do to complete this question is tell me what is the new power of x when this x cubed comes inside. And it's not x to the 3n. It's not that. What would it be?
X to the n plus 3.
Are you comfortable then about any fraction that has 1 minus x on the bottom? Whether you put a 10 or an x cubed. Couldn't I have put 10x cubed here, right? In fact, since I've got it, let's do it. 10x cubed. Wouldn't that be the only difference? Right. So that's a good start, right? We now have power series, Taylor series, for fractions that look like that. Let's do some questions that involve substitution. So I want to find the power series of 5 over 1 minus x squared. I'm going to call it 5 times 1 minus x squared. Now, this is the guy I'm going to use, 1 minus x. But I'm going to use it on 1 minus x squared, okay? What will I replace this x by to generate this fraction? I got 1 minus x here. I want 1 minus x squared. What would I replace this x by to make that happen? Nobody sure? Probably the way I'm phrasing it.
You?
No, I am phrasing it badly. Okay, you replace it by x squared. Were you trying to make it much harder because of the way I phrased it probably? You replace, right, this x with x squared. So you now get x squared to the power of n. Does that make sense? Now, if it was 1 over 1 minus x cubed, wouldn't I put an x cubed here? If it was 1 over 1 minus x to the 40th, wouldn't I put x to the power of 40 here? Now let's see what that looks like when you kind of tidy it up a little bit. X squared to the power of n becomes x to the 2n. So there's your power series for that fraction. I need to do more of those, I'm sure. Okay. How about 2x cubed over 1 minus x to the 4? I'll put up here the guy I'm going to be using. I'm going to be doing some substitution with this guy. It's going to be 2x cubed times 1 take away x to the 4. So it's going to be 2x cubed times. Okay. What do you replace this x by to get this guy?
X to the 4.
Right. And the x to the 4, right, is here, squared. Aren't you looking at x here as a placeholder? It's just a place where things go, right? 1 minus x is just 1 minus, put some here. So if you put x squared here, you get this guy. If you put x to the 4 here, don't you get this guy? Now, taking this a little bit slower. Don't know what that is doing there, it's an n. So we are going to have x to the 4n. This 2x cubed is now going to be brought inside. And that means you're going to get 2. What will be the power of x when an x cubed and an x to the 4n plus 1 get combined?
X to the 4n plus 3.
Agreed. Do you see, with a little bit of algebra and some substitution, can't we find power series for quite weird looking functions? Right. I'm going to switch over to the 1 plus x's because I've realized I haven't done really any of those. I don't want us to get too caught up on just one of the two situations. So using this guy, the -1 to the n is kind of fixed, right? That's just there, right? What will I replace the x by to make that happen? 1 plus x, 1 plus 5x. What will I replace the x by this time?
5x.
So, okay. So if it was 1 plus 10x, wouldn't the x be replaced by 10? Or 10x, right? So that has now got to be made pretty. Style points. A lot of people think that that's good enough, but there is a rule for power series. You must separate out the terms and only have x to the power of something. Not 5x to the power of something, but x to the power of something. So I can take this and split it as a 5 to the n, x to the n, and now style points is happy.
Why do you have to do that?
It's the convention to make everybody write the answer the same way. So power series should always be written as something times x to the 2n, x to the 4n, but it must always be x to the power of whatever n or combination of n's that you use. That is correct in the sense that it's 2/4. This is correct because you've made it pretty and made it a half. So style points are essentially make sure this is separated on its own as a power of x. And it's a convention that we all accept, right? It's a style point rule. That's the way we want you to write them. Okay, I'm going to try and hurt your brain. I'm giving you 1 minute, starting from now, to do that power series. Go for it.
Does it matter whether the constant is on the left or right side of the -1 to the n? What's kind of convention?
The convention should be the -1 to the n goes first.
Okay, that was my instinct, but I wasn't sure if I was right.
That's 5 seconds. Okay, here goes. When you look at something like that, you have to kind of focus on bits. To me, the bit is 10x². Great. And so I kind of know how to deal with that. The next bit is the bottom. If it was 1 plus x, I'd just do that, right? But it's not 1 plus x, it's 1 plus something. And so that x, right, that's there is my something. So that means that I have a substitution to make. So it's not x to the n, it's something to the n. Great. Substitution. That 4x³ is the something. Now, you have this fella. Separate that out, you get 4 to the n. This guy, you get 3 to the n. And then if you bring these pieces inside, so that if it's at all possible, you should do that, you get that fella. You might have to do what I've just done. Do you notice I've tried to write the 10 and the 4 in such a way that people won't think it's 104? And there are a couple of ways to do that. You can stick a bracket around it, or you can put multiplication symbol in. But our convention is that the -1 to the n should always go first, and the powers of x should always go last, and then basically from simplest to ugliest after that. Are you you comfortable with that guy? My gut feeling is that this one has a radius of convergence of 1/4, and the interval of convergence is -1/4 to +1/4. And you don't use the endpoints, but you could check that yourself.
Would multiplying the 10 into the 4n, so it would be 40n times.
Not allowed, unfortunately. It has to be 10 to the n times 4 to the n to become a 40 to the n. And it's not, it's just a single 10, so it's not allowed. That makes sense? Yeah, okay. So let's put, sometimes the simplest ones are the worst. So let's do a 1/9 plus x. And you might think, hey, that's simple. There's only a 9 there, right? There's nothing on the top to worry about. And 9 plus x is very similar looking to that, but the difference is the 9. This is not easy. It is not obvious. You might think that this 9 is unimportant, in which case you just write that answer down. You might think that this 9 is just a 9th, so you just stick like a 9th there. Neither of those are true. It's messier, much messier than that. This is how you have to tackle it. You have to factor out a 9 from the bottom. Although that's not a normal thing to do, the reason why you need to do it is that this thing here, right, what I'm pointing at, this bit here, has to be 1 plus somebody, right? It can't be 9 plus somebody or 2 plus somebody. It must be 1 plus somebody because this is 1 plus somebody, right? So what you would then do, and maybe you don't need this line, but I'm going to do it, is that you separate it out like that. That means I can now do a substitution. What's this x, this thing, going to get replaced by in this fraction? Because think of that as a placeholder where you put stuff. What are you going to put?
One ninth x to the n.
Agreed. 1 plus x squared gets you an x squared. 1 plus 4x gets you 4x, right? 1 plus a 9, you know, whatever, a 9th gets you 1/9 x. And so we have, and again, I'm taking this slowly. You probably don't need all the lines. We have to make this look pretty. Now, this fella can come out as a 1/9 to the power of n and an x to the n. That is allowed because, you know, both of them inside the power can separate. Now, couldn't I take these two guys and put them back in if for some reason I wanted to? I don't want to, but I could do it, right? So that's allowed. And then I'm going to do some more tidying up. Technically speaking, 1/9 to the power of n is kind of in that grey area. I can imagine that it would be accepted in a lot of situations, and then it might not be in other situations. So I'm going for the more rigorous version of style points. If you simplify that down, don't you get 1 to the n over 9 to the n times x to the n? And again, I'm putting every line I can think of in my working. Doesn't that just become 1 over that? Now, when you bring in the last piece of the puzzle, which in this case is just a 1/9, what happens when this 1/9 comes in here? What do you get? When you merge these two together, what do you get?
9 to the n plus 1.
Yeah. When you look at that, isn't it a prettier fraction than it would be with this kind of, you know, this is kind of ugly-ish, right? And this is a little bit more elegant. Would you agree? Maybe you won't, but
No.
it is a little bit more elegant. Kel, question.
How did you go from 9 to plus 1? Oh, never mind. I see that. You multiply
You got
them.
it? Yeah. Multiply them together.
I have a question at the beginning.
Yes.
Could you have split it into 1 plus 8 plus x, like something we'd done previously?
Oh, so you're thinking of just calling it 1, try to think of it. 1, oh, an 8 plus a 1 plus an x.
Yeah.
Yeah, you wouldn't be able to get much out of that because then you don't have this structure, which is what we're trying to get. You'd have two numbers plus an x and not a single number plus an x. So you're really not able to do any other version of what I've just described, except by this really ugly way of doing it. But it's the only way that works. Right? And the reason for that is, have you noticed that I've still got two terms and it's a 1 plus somebody? If you
Yeah.
called it 8 plus 1 plus x, what's that 8 doing? Isn't that still a problem?
Yeah.
And
Okay, that makes sense.
You can't really fix it.
Thank you.
Okay, let's do another one of these, but let's go back to the minuses. I've kind of missed my minuses for a while. So I'm going to do 4x squared over 1 take away 4x cubed. So we're really getting to the ugly ones here. So 4x squared times 1 over. What common factor will I pull out of this expression to allow me to eventually get sigma notation being used? Oh, what? Rebind that. Now, I can ask the question. What ugly factor do I pull out of this so that we can use this sigma notation?
You'd still pull out the 9.
You still have to pull out a 9. And that leaves you with 1 take away 4/9 x cubed. Now, this is like the ultimate ugly, right? The vast majority of them won't be anywhere near as bad as this one, right? But it's that usual thing. If you can do the worst kind, you can do all the others, right? So this is like the worst kind scenario, right? So first problem, 4x squared. Yeah, we're used to that. Second problem, that 9 ain't any good. So I pull it out as a common factor. And are you comfortable with what's left? Okay. This guy here is very important. Isn't he the guy that's going to go here? Isn't he the substitution piece? Right, it's 1 take away something, right? 1 take away something, the something is going to be 4/9 x cubed. So we now have 4x squared sigma I equals 0 to infinity. I'm going to pull out that 9th. And that just leaves me with this guy. So it's 4/9 x cubed to the n, right? I guess I could have done another line, but are you happy with that 1/9 being pulled out so that all we're left with is this guy, and this guy gets me that? Okay, so I now have 4/9 x squared. This fella becomes a 4 to the 9, an x to the 3n, and a 9 to the n. Are you comfortable with that algebra? That 4/9 x cubed all to the power of n can separate as a 4n, an x to the 3n, and a 9 to the n. We good? Last step, and these guys going to merge inside now. That 4 joins this guy, so you get 4 to the power of n plus 1. That 9 joins that guy, you get 9 to the n plus 1. And that x squared times this guy gets you 3n, 2 more added. There is your power series for this particular fraction. Are you slowly beginning to get a feel for how this substitution stroke algebra trick works? How you can take fractions and make essentially power series. Do you know a lot of the power series that we've been dealing with in the previous section? Do you know they came from fractions? Do you recognize these as similar to some of the things you've seen? Well, I think to finish with, and this particular topic, is I'll find one of the homework questions that looks really ugly and let you deal with it. I've just written it the other way around because I prefer it that way around. Okay, you've got 3 minutes to do that, guy. And once you've finished doing it, why don't you put your name in for attendance at the end of it? And if you get this one correct, there is nothing that you can possibly worry about in any of the homework questions, because this is one of the horrible ones. For those who need a little help, there's the first step.
Professor,
Yes.
I was wondering on the last one we just did, for the 4/9 hint,
Mm-hmm.
that was on the left of the sigma.
This one here?
2 lines down. The
Here?
4/9 x. Yeah, that
Right.
that right there.
Mm-hmm. How did I get from here to here?
No, I'm wondering
Oh.
where it went after afterwards.
Oh, what happened is I brought this 4 inside and added 1 to that pair. I brought this x squared inside and added 2 to that. And I brought this 9 inside and added 1 to that.
That makes sense. Thank you.
Okay. Well, based on the chats, 7 of you have finished. Oh, 9 of you are finished. You got about 30 seconds. Hopefully the rest will catch before the end. Okay, it's time up. Let's see how we go. The 81's the problem. I pulled it out and got this, right? You've seen this twice now, so that's the 3rd time. Cool. So this guy on the right-hand side is going to be our, which one? Well, I can't have here. Isn't that going to be the 1 plus x squared guy? Right. So we know that the x is going to be replaced by this. So hopefully you had 1 over 81 x to the 4 to the end. Does that look good? Right. And now we have x squared over 81. If you separate this out, you would get that. You comfortable with that? And I forgot something, didn't I?
The -1 to the end, right?
I did, yes. Glad I caught it in time. And lastly, don't you just merge these guys in? Add 2 to the power on that side and add 1 on that side. For extra special brownie points, I've not mentioned this or gave you any help whatsoever. Is there another way of writing 81 to the power of n plus 1 that could be done? And if you didn't do this, it's totally fine. And if you didn't do it in the test, it's totally fine. But there is a different way of writing 81 to the power of n plus 1, which would be in some places, if they were really nitpicky, be considered better form.
Would it be 9 squared to the power of n plus 1?
And that would then turn into that.
9 to the 2n plus 2, yeah.
So that, well done, you get the brownie points for that one, right? But don't worry if you didn't see that, because that's, I'm never going to pick on that. I don't think that's fair. Right, to finish with, have we got to the point now where we are comfortable, I hope, that certain fractions can be turned into power series? Matthew, question.
Couldn't you then turn that into 3 to the 4 and plus 4?
Oh,
Good point.
good one. Guess who gets even more brownie points? So I'm taking all yours away from you, Kira, and I'm giving them to Matthew.
Fair enough, you earned them.
And in fact, Matthew gets extra brownie points because I didn't see that one either. So would you agree that's even more nitpicky than that one was? Right? So getting to there is kind of where we'd expect you to do. But you know, that was good. I never noticed that. Okay, bye-bye guys. I'll hang about for any questions.
Thank you. Have a good day.
You too.
I had a question about all the homework questions. So on so after we find the series on what was it called, the power series, how do we find the interval of convergence? Or is it just use the ratio test like we always do?
The interval of convergence comes from the you've done. I'm assuming that you've done the radius of convergence so that you found it, right? Now, if you've not done that, then you use the ratio test to find that value, right?
Okay.
So let's pretend you did a question. I'm just going to make one up. Let's suppose, if I can find the darn page, there we go. Let's suppose you did n equals 0 to infinity, and let's just pick that guy, right? Let's suppose we did that one because he's very simple to do. You would do the ratio test, right? The limit is n tends to infinity of an plus 1 over an. And can you trust me that eventually you get that? That's what the answer looks like. Now, it will converge when the limit is less than 1. This number that you have here is called the radius of convergence, r equals. And you must make sure that this is the absolute value of x. If you get the absolute value, a different question, if it ends up being the absolute value of 3x has to be less than 1, then you do that to it. And now you have the radius of convergence. So once you've got the radius of convergence, the interval of convergence in this case is simply just the values of x that this is true for. In this case, because it's a Taylor series, a Maclaurin series, it's that guy. That is our interval of convergence. But we still test the two endpoints. And when you test the endpoints, you go back to the original series, you plug in x is 1 or -1, and you look at that series, and if it converges, then you'll put a square bracket around it saying you can use that number. And if it diverges, you leave it as curved. So you always get this fella first, and once you've got this fella here, you can then use it to create the interval of convergence. And remember to test the two endpoints, because depends on the question. I've seen ones where both endpoints are usable, right? So you put a square bracket on them. But maybe only x equals 1 works and -1 doesn't, and so on.
All right, and then for the problem that you did on the left side on the page that we did as a class, would we just do the exact same thing for the interval convergence?
Today we didn't really do any radius or intervals we're talking about except the first question. So I'm not sure what you mean, Alec. Are you talking about what would I do with this example, for instance?
Yeah, because on the homework we're supposed to find the power series, and then we're supposed to determine the interval convergence afterwards.
So you're going to have to do the ratio test, right? The limit of n plus 1, and do that. You're going to get some more interesting answers because you will find that you get sometimes things like this, right? The limit, right? Well, that's the same thing as that, so it's not a big deal.
Oh, okay.
Right. So that's your goal, right? So if the thing you've got doesn't quite look like that, you make it. You could get 2x squared less than 1. Well, I would do absolute value of x squared is less than a half. And then the absolute value of x is less than the square root of a half. So you see that one would actually be quite weird looking.
Yeah.
Right. So yeah, that's how you do it. Limits, the ratio test using limits, and then you solve eventually for the absolute value of x less than a number. I should do some of those probably tomorrow because I didn't even spend any time on those, but I'll try and remember. Maggie, you going to be here tomorrow?
Yeah.
Right, Maggie, your job is to tell Alexander to remind me to do radius and intervals of convergence. You got that?
Oh boy.
Right. Alexander, you have two jobs. Your
I got
first
two?
job, yeah, is to remind me to do radius and intervals convergence. And your second job is to remind Maggie that she's to remind you.
Okay.
Okay, so somewhere between all those combinations, won't one of you remember to tell somebody?
Yeah.
Okay, any other questions?
I have a real quick question.
Mhm.
How can you tell for like some of the problems we just did, how can you tell if they're a Taylor series or a Maclaurin series?
All the ones we've done so far all end up being x to the power of stuff. So they're all going to be Maclaurins. None of them are Taylors. To be Taylors, it has to be in brackets x minus 1 squared. So a power series that's a Taylor's would have things like x minus 1 to the n, or 2 to the n, x plus 3 to the n. That is what makes it a Taylor series. The ones that we are dealing with all look like this, don't they? But they all just have x's, and that's what makes them Maclaurin series. Does that make sense?
Yes, thank you.
I have a question real quick.
Dylan, what you got?
So on the previous day's homework, 11.8, yeah, 11.8.
Okay.
My
Oh.
gut reaction for whether it converges or diverges has been wrong multiple times. So I just want
Okay.
to know if there's a tip or a trick that I seem to be missing.
Let's see, 11.8. I'm just clicking on that guy. See what's going on here. Just trying to remember what's in this list. So your question, is there a tip or a trick?
So like with the interval, like once you do the test to see if like say
Right, so you found the radius and now you've got the interval of convergence. And I'm assuming then, is your problem that your endpoints aren't always right? You
no,
think
just that like I think it converges, but it actually diverges because it looks like yeah. So just getting those two mixed up.
Right, let me be specific here. When you're saying converges or diverges, is that for specific values of x?
Yes.
Okay, so when you've got your series, whatever it might look like, for instance, in this case, and let's suppose one of the endpoints was 1, and pretty typically the other one would be -1. Your first thing you have to do is you actually have to plug in 1.
Yep.
So when I get that 1 to the n over n cubed, right? Well, 1 to the n doesn't matter, it's always 1. So it means that this guy looks like that. And so I just base my decision on all the other series that we've done in the past. When I see that one, I see an alternating series where the bottom gets smaller and it goes to 0. So I'm doing basically the alternating series test in my head. I know that that converges.
Ah, okay, I see.
Right. Now, if I had an alternating series that looked like that, same thing. But if I had an alternating series that looked like that, I know it diverges. And how do I know it? That doesn't tend to 0, right? That's also increasing, which is both of those will kill it, right? On the other hand, if there's no -1s involved, I might be looking at a p-series. And that p-series I know converges. And very often you get a kind of negative version of the same guy like that. That's an alternating series, but if that converges, doesn't that kind of automatically converge?
Yeah.
So I get 2 for the price of 1 in that case. But there's no shortcut. But it kind of depends on what you get, because don't you sometimes get, oh, I don't know, do you really get them? I guess you could. You could get something, like that, right? A really messy one, right? If I was looking at that, then I'd have to be, put a +1 in here. Wouldn't I be looking at a geometric series? And therefore I would say, oh, geometric series, I can see who you are.
Yeah. Okay. That's a big help. Thank you.
Okay.